You're in a primary school art lesson, and your teacher is talking about vanishing points. You're drawing a street, a railway track, whatever. Two long parallel lines trailing off into the distance, never to meet. But your teacher stops you. You see how these lines, they say, look like a ladder in front of you. You need to angle them like this, just like a real track. But how can this be? They're parallel, and parallel lines can't meet, and by definition, a line has no endpoints. So something is clearly wrong, right? So you test this. Take a picture of the track. Surely that must be right. Honestly, what did you expect? Instead, you think, what is a photo really? Because it's not the perfect representation of a scene. Near things look bigger, far things look smaller. You have a solid 3D scene getting projected into a flat 2D image. Even if you take a 2D image and project that, you can still skew it all sorts of ways. Looking at these two diagrams, one a projection of the other, we can see that they look quite different. How do we know that they're still the same thing? Well, some things don't change. A line is still a line, and a circle is, well, not a circle, but maybe an ellipse, or a parabola or a hyperbola. They're all in this general class of curves called conics, so we'll go with that. Conics stay conics. But obviously that's not enough. What about lengths? Look at these 4 points on the line, or buildings if you like, since we needed physical analogies. Call them A, B, X, and Y. Let's look at the distances between the points, and we take this ratio, AX over BX, to AY over BY. We call this the cross ratio of the 4 points. Why is this important? Well, it turns out that this cross ratio stays the same after projections, so we can use it to find the length of this street. If we know how far apart these buildings are, we can work out where this last one is. But how does this work? First, a quick refresher on signs. If we have a right-angled triangle in a circle with diameter 1, then the sine of an angle just means the length of this short side. But here's the neat bit. We can slide these points around the circle, and the angle and side stay the same. So, for a fixed triangle, the sine is proportional to this side length. We call this sine rule. Now we pick a random other point. So we have 4 intersecting lines, which we call a pencil. We notice this cross ratio also applies for the sines of these angles. Use sine rule to prove it yourself, if you like. This means the ratio only depends on the angles. So we can move the line around, but the angles and so the ratio stay the same. But it also means that we can move the extra point around and this still holds. This basically means that we can project the cross ratio around wherever we want and its value will stay the same. Something quite neat happens when this ratio is exactly 1. In other words, left times right equals in times out. Then we call this a harmonic pencil. And as it turns out, these are actually really common. Let's think about an interesting one. We want to choose x and y so that ax equals bx and ay equals by. So x is the midpoint of a and b, and y is outside both of them, but how can this be? We want these lengths to be equal, but obviously that's not possible. When we drag this point away, though, both lengths will increase at the same rate and they get proportionally closer, so the last point y is infinitely far away. Now these have to be parallel lines, so they never really meet, right? But from a train track example, we can see that they meet eventually, so there has to be some sort of hypothetical intersection. In projective geometry, this is actually a real point that we can use, and we call it a point at infinity. In fact, every direction of line has its own point at infinity. A more intuitive way to think about this is using a parallelogram. If we connect the midpoints of the opposite sides and then connect the diagonals like this, we get the same pencil. We can prove this with sine rule too. In fact, all harmonic pencils look like this because we can always construct a parallelogram using 3 of the lines, and the 4th one has to go here because only one line can make this harmonic. Harmonic pencils are actually really versatile, and there's plenty of scenarios where you can find them. If you have a right angle and these two angles are equal, for instance, the parallelogram is just a rectangle. Of course it's a pencil. Or take a triangle with a point and shoot these lines through it. Hey, another pencil. Or take a circle, add some tangents, pick a line, another one. Point is, they're common, you just need to know where to look. So this concludes my simple introduction to projective geometry. If you're interested, try Evan Chen's quintessential EGMO for some actual resources. To end off, I'll leave you all with this simple problem which can be solved with harmonics. Email me your solution for a chocolate. Thank you!